October 26, 2025. Without warning, a new batch of official images of 3I Atlas appeared on NASA's Deep Archive servers, time-stamped, verified, and quietly published at 2:17 UTC. No press release, no headlines, no announcement. Yet within hours, those who found them realized something was wrong. The object in the images doesn't look like anything that had been described before. For months, astronomers have tracked 3I Atlas as an interstellar visitor, a body that doesn't behave like a comet, doesn't reflect light like an asteroid, and doesn't fit into any known category. But these latest frames defy even that uncertainty. The surface geometry seems fractured, metallic, and asymmetrical. The glow that surrounds it, not a dust coma, not reflected light, but something closer to controlled luminescence. Across observatories, the data triggered quiet disbelief. A handful of analysts at Arecibo's successor network noticed strange repeating streaks in the spectrograms, like pulse trains, evenly spaced, not noise. Meanwhile, temperature readings from the infrared channel came back far higher than solar heating alone could explain. No agency has offered a statement yet, but from the metadata, one thing is clear. These aren't artist impressions. They are direct captures, multiband, real, and recent. And that means one unsettling thing. Whatever 3I Atlas is, we're finally seeing it up close, and it's not what anyone expected. Now the real question begins, what exactly are we looking at? At 2:17 UTC, October 26, 2025, a new dataset quietly appeared inside NASA's planetary data system under the tag Atlas 3 VIS SPC 2025-1023 AW. Within minutes, automated scrapers mirrored it to public nodes, and that's when the first researchers began to notice the anomaly. The files contained 7 full-spectrum images, visible, infrared, and ultraviolet, all captured within a 4-hour observational window between October 23rd and 24th, using a combination of the Hubble Wide Field Camera 3, JWST's NIRCam, and ESA's Solar Orbiter Heliospheric Imager. The dataset was supposed to be routine. For months, both agencies had been archiving imagery from 3I Atlas's inbound trajectory, part of a cross-mission calibration exercise meant to test long-range tracking and deep space alignment. But when the images were opened, the structure and frame didn't match any known morphology. In the visible band, 3I Atlas appeared enormously elongated, almost teardrop-shaped, with what looked like a fissure running diagonally across its midsection. The sunlight reflecting off its body didn't scatter in the chaotic way that dust or ice normally would. Instead, the reflections followed a consistent angular pattern, suggesting an unusually smooth and possibly metallic surface beneath the darker crust. The infrared channels were even stranger. Analysts found heat gradients across narrow linear segments, indicating localized warming, as if small regions were being heated internally rather than by the sun. The temperature variance exceeded 140 Kelvin between adjacent points on the same structure, an impossible value for a natural body of this size. Normally, comets show thermal distribution that follows sunlight exposure. Here, the heat bands were perpendicular to the solar vector. The UV imagery processed by instruments revealed ionized jets, not broad chaotic sprays, but thin focused streams of light blue material emanating from specific points on the surface. They appeared to pulsate at regular intervals. In 2 frames, separated by 26 minutes, the emission frequency was identical to within 1%. A natural sublimation process cannot do that. When the raw FITS files were examined, some researchers noticed something else. The stars behind the object appeared slightly displaced, as if light near the object was bending. The deviation was minor, around 0.08 arcseconds, but enough to raise questions about whether 3I Atlas is interacting with its surrounding plasma field in a way that affects the propagation of light itself. By sunrise in Europe, astrophysicists from Madrid, Bologna, and Cape Town had already pulled the images for independent verification. Every checksum matched. No sign of tampering, compression, or simulated artifacting. These were authentic. Then came the most important discovery, the metadata timestamps. Each image corresponded to a very specific moment in the object's trajectory, roughly 0.48 astronomical units from the Sun, moving at 64 kilometers and positioned near the solar ecliptic with a low inclination of just 4.1 degrees. That means the images were captured during a near-perfect viewing angle, an opportunity window that will not occur again before it passes behind the Sun on October 29th. And here's the detail that few noticed at first. The naming convention in the archive entry wasn't standard. Normally, NASA uses a simple mission prefix like JWST-PSPs, followed by date and sequence. But here a suffix appeared, INT-MODEX. No one outside the agency knows what it means. Informally, analysts have speculated it stands for Integrated Mode Experiment, a data-sharing test across instruments. But to others, it looked like an internal tag for an intentional experiment, perhaps something that wasn't meant to be seen until after conjunction. As the hours passed, astronomers around the world began comparing the new images with those from September and early October. The differences were staggering. The albedo pattern, the way the object reflects light, had shifted drastically, almost as though the surface had reconfigured. Areas that were once dim were now radiant, while the previously bright regions had gone dark. Could this be rotation? Maybe. But that would require a complete reorientation of the body's axis in less than 4 weeks, something no natural comet of this size could achieve without external torque. And then came the most chilling realization. In one of the near-infrared composites, faint glints could be seen along the fissure line. They were small, evenly spaced and aligned, like points of emission or reflection. When enhanced through gradient mapping, they appeared as discrete nodes, each separated by roughly 120 Malmsmers, perfectly consistent spacing. No natural fracture does that. As the images circulated across research networks, the consensus split sharply. Some argued it's an optical illusion, perhaps pixel interpolation from the imaging process. Others weren't so sure. The brightness intervals followed a periodic sequence, not random noise, and the timing couldn't have been worse or more deliberate. With just 3 days before solar conjunction, these might be the last unobstructed images humanity receives of 3I Atlas for months. So the question now isn't just what the images show, it's why they were released now, with no explanation, and what someone might be trying to tell us before the object disappears behind the Sun. Within the first hour of the release, private research channels began lighting up. A message from the European Space Imaging Network simply read, "Is this a calibration artifact?" Others followed. "Impossible albedo symmetry. Surface shouldn't look that reflective. Does anyone else see the internal band?" By 040 UTC, the community split into 2 camps, those calling it a misinterpretation and those convinced something had changed physically in 3I Atlas since the last observation window. Among them was Dr. Helena Braun, a senior analyst with the Max Planck Institute, who posted a frame-by-frame analysis comparing the new images to the late September captures. Her verdict was cautious but clear. We are not looking at the same surface. The object's visual texture was almost surgical in its precision. It wasn't the chaotic mosaic of ice and silicate dust typical of comets. It was layered like composite material. At a glance, it resembled obsidian, streaked with veins of glowing blue. But under high-contrast rendering, those veins formed patterns, not fractures, clean, angular intersections forming near geometric nodes. NASA's internal reaction was unusually restrained. No public statement, only a brief notation added to the metadata summary. Visual irregularities under review. That's bureaucratic shorthand for "we don't know what we're looking at." By dawn, a few astronomers tried to calm the growing speculation. They proposed mundane explanations: overexposure, solar interference, motion blur. But those theories collapsed quickly when multiple independent observatories reported the same geometry captured from slightly different vectors. Even the Japanese Subaru telescope in Hawaii, which wasn't part of the original mission network, logged an identical silhouette. Then came the color anomaly across all imaging platforms. 3i Atlas exhibited a distinct nickel blue emission, a hue most commonly associated with ionized nickel gas, not reflected light. The emission line at 341 nanometers matched that signature perfectly. Yet, there was no apparent outgassing, no visible plume. The glow seemed to originate beneath the surface, diffusing outward through the object's fractured shell. Astrophysicists who examined the light curves noticed something else. The reflections weren't random. Every rotation, the same glints reappeared, precisely timed, as if part of a repeating cycle. If that timing is accurate, it means the object rotates every 11.42 hours, significantly slower than earlier estimates of around 6. That alone would imply that some external force, possibly controlled torque or active venting, altered its rotation. But that's not the only inconsistency. The shadow geometry didn't match the sun's position. In 2 frames, shadows on the lower curvature bend away from the solar vector, which should be physically impossible unless the surface is concave or light is being refracted. As the data circulated, the disbelief turned to quiet alarm. In a closed session at the Harvard-Smithsonian Astrophysical Center, a senior researcher reportedly said, "If these images are genuine, we may be seeing engineered surface behavior, not geology." Yet others urged restraint. A counter-report from the Institut d'Astrophysique suggested a less extraordinary cause: layered mineral sublimation. When metallic volatiles heat unevenly, they can form glowing fissures that mimic structured light. But the problem with that explanation is simple: the pattern symmetry. The fissures aren't random. They're parallel. They repeat. In the background, a few data analysts began cross-referencing the release time with telescope telemetry logs. What they found raised even more questions. The exact timestamp of NASA's file upload coincided with a minor magnetic fluctuation detected by the Parker Solar Probe, a 0.04 Gauss spike recorded at 2:16:53 UTC, just 20 seconds before the first file appeared online. Coincidence? Possibly. But for those tracking 3i Atlas's influence on solar wind behavior, it added an eerie layer to the story. By midday, the first enhanced composites began circulating online. Independent renderings exaggerated the blue luminescence, revealing what looked like striations, long, narrow ridges that wrapped around the nucleus like ribs. Some viewers called them panels, others plates. It wasn't long before speculation crossed into public view. A retired ESA engineer posting under an anonymous handle wrote, "The reflection angles suggest planar surfaces. That's not natural, not if they are equidistant." Still, the mainstream outlets stayed silent. Only a handful of science blogs picked up the anomaly, carefully avoiding the word artificial. For the analysts, the question wasn't whether the images were real. They were. The question was why the object now looked engineered. If 3i Atlas has always been this shape, why didn't earlier scans reveal it? If it recently changed, what force could reshape a body traveling at 64 km/s? The early consensus: neither possibility is comforting, because if these images are accurate, something on or within 3i Atlas is active, either responding to solar proximity or doing something timed precisely before it disappears behind the sun. And if that's true, the next discovery would only deepen the confusion, because the object, as shape itself, makes no sense in the context of known celestial mechanics. When analysts first attempted to overlay the October 23rd images with earlier radar profiles, nothing aligned. The original physical model, built from a mix of ground-based and spaceborne data, depicted a moderately elongated body, roughly 1.6 kilometers long, with an irregular asymmetrical curvature typical for interstellar debris. But the new images show a shape that is not irregular at all. The silhouette is precise, defined, and unnervingly consistent. It curves inward like a crescent or broken ring with a hollow inner edge, glowing faintly in nickel blue. The outer contour remains shadowed, jagged, but coherent, as though carved or manufactured. Measurements from the pixel ratio suggest the structure now spans over 2.3 kilometers, with an internal cavity roughly 700 meters wide, far larger than the original estimates. Immediately the question arose: how could an object whose apparent size and structure change so drastically within a matter of weeks? The simplest explanation, and the one most agencies are quietly holding on to, is image misinterpretation. The theory suggests that lighting conditions, camera alignment, or overlapping jets could have created the illusion of a hollow shape. But the numbers don't support it. The same curvature appears across multiple instruments: JWST's NIRCam, Hubble's WFC3, and solar orbiter's HI2, each operating at different wavelengths, distances, and angles. Their independent perspectives confirm the same outline. If this isn't a trick of light, then something else happened between early October and now. One hypothesis points to fragmentation, a common process where comets split under thermal stress, yet no debris field has been detected. The solar wind sensors aboard the Parker Solar Probe and SOHO show no sudden increase in particulate density. No plume, no trail, no evidence of disintegration. Instead, the internal reflection pattern suggests a structural rearrangement. Something within the object appears to have shifted, possibly exposing an inner layer. The faint blue glow emerging from the concave region seems uniform, not scattered, not chaotic. When analysts applied spectral decomposition to the dataset, they found an emission pattern following a 1.3 micron wavelength modulation repeating every 9.6 seconds. Natural rotation cannot produce that. In other words, the object's internal geometry is emitting light rhythmically. That's when the modeling teams hit a wall. Conventional comet composition, silicates, ices, carbonaceous material cannot produce coherent emission at those frequencies. The only known materials that can are metallic compounds under controlled ionization. Specifically, nickel tetracarbonyl, the same compound earlier spectrograms hinted at months ago, can emit light under thermal breakdown near that frequency range. But even that explanation falls apart under one detail. Nickel tetracarbonyl decomposes rapidly in sunlight. At 0.48 astronomical units, it wouldn't last seconds, let alone days. So either something is continuously replenishing that emission, or it isn't chemical at all. The University of Bologna's Exoplanet Imaging Lab ran simulations comparing the current silhouette to all previously known comet morphologies, including the bifurcated nucleus of 67P Churyumov-Gerasimenko. The program returned a confidence ratio of less than 1.8% that 3i Atlas fits any natural category. The anomaly is too smooth, too proportionate, and too internally coherent. Here's where it becomes more perplexing. The shadow curvature across the object suggests it's hollow on one side, a concave depression reflecting light differently depending on angle. Normally, that would imply a catastrophic impact or collapse, but the uniform reflection across that inner curve contradicts any idea of destruction. It looks deliberate. When the model was rendered in 3 dimensions, analysts noticed a pattern that left them silent for several minutes. The curvature matched the golden ratio spiral within 0.5% deviation. That doesn't occur in nature at this scale, especially not in bodies traveling between stars. In an internal email leaked from one of ESA's review sessions, an unnamed optical engineer reportedly wrote, "The geometry looks designed for something, reflection, collection, or emission. I can't prove that yet, but I can't explain it any other way." The official stance remains cautious. NASA's External Communications Directorate issued a two-sentence note on the morning of October 26th. The latest imagery of 3I Atlas provides valuable data for understanding non-gravitational forces acting on interstellar objects. Image interpretation continues. But within the research community, there's growing unease. If the structure is truly as symmetrical as the images indicate, then the implications are staggering. It would suggest that 3I Atlas isn't a random shard of interstellar debris. It's something engineered, either by nature under unknown conditions or by something that understands geometry better than we do. And yet, there's one more layer of contradiction. The object is surface temperature derived from the same dataset doesn't match what that structure should allow. The next chapter examines the numbers behind that inconsistency and why they might prove that 3I Atlas isn't just reflecting sunlight, it's generating heat. When the temperature data from the October 23rd sequence was first decoded, analysts expected confirmation of a known pattern at 0.48 astronomical units. The solar flux should produce surface temperatures near 390 Kelvin, enough to sublimate volatile compounds, release gas, and trigger outgassing jets. Instead, the data revealed something else entirely. Narrow zones of localized heat reaching up to 730 Kelvin, bordered by regions at less than 150. It wasn't the gradient itself that alarmed scientists. It was the precision. In natural bodies, heat spreads diffusively. Solar energy strikes, and the material conducts it irregularly through porous ice and dust. But 3I Atlas exhibits sharp boundaries, like thermal fences separating one temperature band from the next. That detail alone implies active thermal regulation. Dr. Noah Reed of Caltech's Infrared Processing Center was among the first to run gradient analyses on the JWST infrared dataset. His conclusion, quietly circulated in an internal memo, was striking. These readings are quantized. We are looking at discrete thermal zones, not a continuous gradient. That does not happen in nature. The highest temperature regions correspond precisely to the fissure running across the object's center, the same area emitting the faint nickel-blue light seen in visible wavelengths. When scientists compared the heat pattern to the emission frequency, they found a perfect correlation. Every time the glow pulse intensified, infrared brightness spiked by 6%. That means the heat source is internal and rhythmic. In other words, 3I Atlas isn't being heated by the sun, it's heating itself. For skeptics, that statement borders on heresy. No known interstellar object has ever demonstrated internal power generation. Yet, the data leaves little room for alternative interpretation. Some propose that internal outgassing vents could concentrate heat temporarily, but even that fails to explain the symmetry. The thermal zones are evenly distributed along a spiral pattern, wrapping around the nucleus like an engineered coil. A closer look at the spectral signature deepens the mystery. The emission lines at 4.67 microns correspond to carbonyl compounds breaking apart, a plausible source of thermal reaction. But the peaks are too narrow, almost laser-like. Natural outgassing produces wide, messy bands. Here, the lines are crisp, directed, controlled. There's also the question of stability. Since early August, 3I Atlas has remained remarkably intact despite accelerating solar flux. Most comets fragment long before reaching 0.5 astronomical units. But 3I Atlas shows no measurable erosion, no loss of mass, no new debris cloud. Its albedo ratio has actually increased, suggesting that parts of its surface are regenerating, becoming more reflective with time. That's not how rock behaves, it's how systems behave when they adjust to maintain equilibrium. One hypothesis from ESA's materials division suggests an unknown reaction similar to endothermic phase transition, where absorbed radiation is temporarily stored, then re-emitted at specific wavelengths. But to achieve such precision, the material would need properties closer to metallic ceramics or photonic composites, substances engineered for heat control. And that's where the conversation becomes quietly uncomfortable. Because if 3I Atlas is composed of engineered material that demands intent, not coincidence, the anomalies don't stop there. The Parker Solar Probe registered faint magnetic fluctuations synchronous with the object's thermal cycles. Every pulse of heat corresponded to a microscopic distortion in the local magnetic field consistent with electromagnetic discharge. It's as if 3I Atlas is generating or manipulating its own magnetic envelope. That would explain another mystery: why the solar wind bends near it. When the object's field stabilizes, it deflects charged particles, creating an invisible cocoon, a behavior previously observed only around magnetized asteroids with metallic cores. Yet 3I Atlas is far too small to sustain a core dynamo. Something else is producing those magnetic fields, and it gets stranger. In 2 frames captured by Solar Orbiter, faint thermal wakes trail behind the object, perfectly linear, extending for thousands of kilometers before fading. Their temperature decay matches plasma cooling, not dust dispersion. If these are exhaust trails, they are neither random nor natural. Privately, mission analysts began referring to the pattern as thermal harmonics. Each pulse, each glow, each magnetic distortion occurs in perfect rhythm, repeating every 9.6 seconds. No natural system maintains that kind of periodicity over hours, not even rotating comets. Some within NASA argue that the heat could stem from piezoelectric effects, where internal stress releases small electrical discharges, but that would require crystalline structures aligned over kilometers, an impossibility for interstellar debris. Others point to unknown chemistry invoking exotic carbon-nickel lattices formed in deep space collisions. But again, that doesn't explain the precision. At this stage, it's not about what heats the object, it's about how that heat behaves. Every spike corresponds to a pulse of light. Every pulse corresponds to a magnetic twitch. It's a perfect triad: heat, light, field, the signature of a coordinated system. By midday, October 26th, that pattern had been confirmed independently by 3 observatories. None of them can yet explain it. And if internal heat generation is confirmed, it changes everything. Because an object that can regulate its own thermal output isn't passive, it's adaptive, which brings the investigation to its next and perhaps most critical discrepancy. The light emitted by 3I Atlas doesn't just illuminate it, it behaves like a signal, one that interacts with its environment in a way no natural reflection should. When the first raw spectral data was decoded, analysts noticed something that made them double-check their instruments. The glow coming from 3I Atlas wasn't random scattering or thermal radiation, it was structured. In every wavelength from visible to near-infrared, the signal showed periodic modulation, faint but mathematically consistent, like an encoded pulse embedded within the light itself. Under normal conditions, reflected sunlight is chaotic. Its intensity fluctuates depending on surface roughness, angle, and dust composition. But when spectrographs from the James Webb Space Telescope, Solar Orbiter, and TESS were cross-compared, a synchronized rhythm appeared. Every 9.6 seconds, the same interval as the thermal pulse, the object's brightness rose and fell in a uniform waveform. That synchronization instantly ruled out coincidence. Researchers first suspected interference from the spacecraft sensors, perhaps a calibration overlap. Yet the pattern persisted across instruments separated by millions of kilometers. Even more unsettling, the amplitude ratio, the difference between peak and trough brightness, was almost identical for all observatories, roughly 3.4%. No random reflection could reproduce such global uniformity. This is when spectral polarization analysis entered the picture. By studying how light waves twist as they travel, scientists can determine the surface composition of an object. What they found was unorthodox. The reflected light from 3I Atlas carried a rotating polarization vector, changing direction every pulse. In simple terms, the light appeared to be spinning in rhythm. That is not a known natural behavior. The only comparable phenomena occur in coherent emission systems, lasers, plasma beacons, or tightly focused radiation bursts where the source controls the phase of light. If that's what this is, then 3I Atlas isn't reflecting the sun's rays, it's modulating them. When NASA's photometry team at Goddard attempted to simulate the readings, the model only fit under one assumption: that the light was being amplified before emission, as if passing through an active medium. Such amplification would require a cavity, a resonant chamber, or at minimum, a material capable of reinforcing specific wavelengths. The fissure observed across the object's midsection could theoretically act as that cavity, a resonator harnessing incident solar energy and re-emitting it in controlled bursts. But what purpose would that serve? If natural, it could represent a previously unknown radiative process where internal compounds ionize and emit harmonics. But if artificial, and that's the word some researchers now whisper privately, it might mean something more deliberate: communication, regulation, or propulsion. Because the modulation isn't random. When frequency analysis was performed on the light curve, discrete harmonics appeared at precise ratios: 1x, 2x, 3x, and 5x of the base pulse. That's not how outgassing works. That's how signaling works. A confidential summary from the Arecibo Legacy Continuation Group phrased it carefully. The observed photometric oscillations resemble controlled emission gating potentially driven by internal resonance systems. Whether natural or synthetic, the structure demonstrates feedback consistent with engineered coherence. Even among skeptics, that line drew silence. Then another anomaly surfaced. In two of the JWST images, a thin halo of faint green light extends several kilometers beyond the object's surface. When brightness values were integrated, the halo's intensity dropped exponentially with distance, but not uniformly. There were wavefront ripples, concentric arcs propagating outward at sublight speeds. Those ripples correspond to solar wind variations recorded by the Parker Solar Probe, meaning the object's light emissions are physically interacting with charged particles streaming from the sun. In effect, 3I Atlas is shaping the plasma environment around itself, carving channels through it like a magnet carving through iron filings. Here's where it turns from anomaly to impossibility. In one frame, captured precisely at 3:11 UTC, the light pulse from 3I Atlas occurred 0.14 seconds before the corresponding magnetic ripple registered on Parker's instruments. For the ripple to appear downstream that quickly, the plasma would need to accelerate at over 10 times the solar wind's base velocity. That means the object isn't just responding to the wind, it's influencing it. Some theorists suggest the glow could be a magneto-hydrodynamic feedback loop, where charged dust interacts with magnetic lines to produce repeating pulses. But no one can explain the precision or the harmonic ratios. Others have speculated it might be a natural plasma sheath resonance similar to auroral emissions. But again, that wouldn't synchronize across instruments millions of kilometers apart. And still, the timing aligns too neatly with the thermal data, the magnetic distortions, and the object's slow rotation. Every layer of observation reinforces the same rhythm. As of tonight, no agency has publicly acknowledged the coherence pattern, but inside private astronomy forums, a quiet term has started circulating: regulated luminescence. It implies what the official reports cannot yet say. that 3I Atlas might be deliberately modulating energy, either as a byproduct of its composition or as an action with intent. If that's true, then the next anomaly could provide the missing link, because the source of that light, the narrow jet seen in the ultraviolet band, behaves less like a cometary vent and more like a controlled exhaust. In natural comets, jets are messy things. When volatile ice heats and vents, the outgassing forms chaotic plumes, spraying particles in all directions. They twist, flicker, and dissipate as the nucleus rotates. But in the October 23rd ultraviolet captures of 3I Atlas, the jet is anything but chaotic. It's precise, controlled, and unnervingly stable. The data show a single narrow plume extending roughly 320 kilometers from the object's lower curvature, not expanding outward, but running parallel to the solar vector aimed directly toward the sun. Every comet known to science ejects material away from solar radiation, driven by pressure and heat. Yet 3I Atlas does the opposite. That simple fact should be impossible. Spectrographic analysis of the jet reveals its composition, a highly ionized stream containing nickel, carbon monoxide, and trace hydrogen. But the emission ratios are off. The nickel signature dominates, nearly 12 times stronger than any cometary jet ever recorded. That's where the mystery deepens. Nickel, particularly in its carbonyl form, should break apart instantly under solar UV radiation. Instead, it remains stable over hours, maintaining a consistent brightness. To achieve that, the material would have to be continuously replenished or shielded by some form of electromagnetic confinement. And that's exactly what the data implies. The jet doesn't diffuse into space as expected. It tapers, then curves back as though magnetically redirected. By mapping the plume across successive frames, scientists at ESA's Solar Physics Division discovered that the jet's apparent angle oscillates every 9.6 seconds, the same rhythm found in its light pulses and thermal surges. The pattern isn't random turbulence, it's synchronized behavior. In a private call between analysts at NASA's Goddard Center and the Italian Space Agency, one engineer reportedly remarked, "It looks like thrust vectoring." He wasn't exaggerating. To test that hypothesis, motion analysts examined the object's micro-trajectory over the past 4 days using solar orbiter parallax data. Yet, 3I Atlas's course remains pristine, the most stable of any interstellar body ever tracked. To make sense of it, a few theorists turned to magnetohydrodynamics. They proposed that the jet might act as a magnetic stabilizer, balancing torques caused by solar radiation pressure. That theory might have worked if the jet weren't aimed at the sun. So, the debate circles back to intent. If the jet is stabilizing the object, it's doing so in the most efficient way possible by countering gravitational shear and maintaining trajectory symmetry. That implies an awareness of external forces, a system that measures, calculates, and adjusts. And as unsettling as that idea sounds, it's not the only behavior hinting at regulation. The same precision that governs its jet appears to control its spin. The object's rotation isn't chaotic. It's smooth, deliberate, and measured. The next chapter examines how a body tumbling through interstellar space could somehow begin to rotate with balance and intent. When researchers first plotted 3I Atlas's rotational data in August, the numbers made sense. The object appeared to spin irregularly, completing one chaotic rotation every 6 hours, a typical behavior for cometary bodies shaped by uneven outgassing. But the new telemetry from late October tells a different story. The spin has slowed, the axis has stabilized, and the motion is too clean to be random. From October 18th to October 24th, high-resolution light curve readings from the Solar Orbiter, JWST, and the Las Cumbres Global Telescope Network were independently synchronized. What they show is startling. 3I Atlas now completes one rotation every 11:42 hours, with a variance of less than 0.2% across 6 observation windows. That level of consistency is impossible without an internal or external mechanism maintaining balance. In comets, spin rates fluctuate constantly due to venting forces and solar torque. Jets erupt, mass shifts, and the object wobbles. But 3I Atlas's spin is locked, almost regulated. Dr. Lucien Morel of the Paris Observatory called it the cleanest rotation signature we've ever seen from a non-gravitationally bound object. The light curve reveals no sign of precession or nutation, no secondary wobble, no random drift. Instead, the object rotates as though it's being actively managed. Then came the shock that pushed this from anomaly to impossibility. During a combined review session between ESA and NASA analysts on October 25th, the group compared the timing of the rotation peaks with the thermal and light modulation cycles observed in previous data sets. The match was perfect. Every time the object completes one full rotation, exactly 4,282 light pulses have occurred. Every time a pulse cycle completes, the object's surface heat distribution resets in near-perfect symmetry. It's as if all three systems, rotation, light, and temperature, are part of one integrated process, a self-correcting one. This synchronicity would require precise feedback control. In spacecraft design, such feedback loops are fundamental. They use gyroscopic sensors or magnetic torque systems to stabilize orientation. No known natural process can produce that triple synchronization spontaneously. Still, skeptics point to one possible loophole: magnetic coupling. If 3I Atlas carries a magnetized core, perhaps an ancient remnant of a metallic planet, interactions with the solar magnetic field could generate a stabilizing torque. But that theory collapses under two facts. The field alignment is constant, even as the solar field shifts daily. The amplitude of the torque matches the jet's rhythm, not the sun's. That means the stabilization isn't external, it's coming from the object itself. A small team at the Italian National Astrophysics Institute performed a dynamic simulation. Their conclusion out was cautious but clear. The rotation is being regulated by periodic mass ejection events from beneath the fissure, microscopic thrust bursts that maintain balance. Yet the problem remains. The required precision is absurd. To maintain such rotational stability, those bursts would need to be timed within milliseconds of the object's motion, impossible without sensors or an intelligent feedback system. The data doesn't just show stability, it shows awareness. Further evidence emerged when ESA's Bepi-Colombo spacecraft positioned near Mercury detected micro-variations in solar wind velocity correlated with the object's spin phase. Each time 3I Atlas completed half a rotation, a tiny surge, just a fraction of a percent, appeared in the plasma density stream. Analysts described it as an invisible signature, like an electromagnetic heartbeat. If this is accurate, it implies that 3I Atlas is not just passively rotating, but interacting with the solar environment during that motion, altering plasma flow in precise intervals. At this stage, one thing is becoming clear. The rotation is neither incidental nor random. It's deliberate, or at least responsive. The system maintaining that spin seems to know when and how to correct itself. In a leaked technical bulletin circulated within NASA's internal channel, an anonymous contributor summarized it in one haunting line: "We're no longer observing a rock, we're observing behavior." That statement was quickly redacted, but by then, the sentiment had spread across every major observatory. 3I Atlas isn't behaving like an inert object. It's acting like something that's aware of balance, heat, light, and trajectory. Yet even this doesn't explain the growing list of anomalies surrounding it. Because as its rotation stabilized, instruments across multiple agencies began detecting faint electromagnetic distortions, ripples spreading through the local space environment. The signals didn't match solar storms nor background cosmic activity. They emanated from a specific source, the space around 3I Atlas itself. And those signals carried a frequency no one expected. When the Parker Solar Probe transmitted its magnetic field data from October 23rd, analysts expected noise. The probe's instruments were being bombarded by solar radiation, and 3I Atlas was still half an astronomical unit away. But inside that chaos, one of Parker's field spectrometers recorded a repeating pulse, a 0.04 Gauss fluctuation cycling every 9.6 seconds, the same timing found in the object's light, heat, and rotation. At first, it was dismissed as telemetry drift, a synchronization error caused by overlapping data packets. Yet cross-checking with ESA's solar orbiter revealed identical periodicity captured at a completely different vector. The signals matched not just in rhythm, but in phase, meaning they rose and fell simultaneously across millions of kilometers of space. That synchronization is impossible under ordinary solar dynamics. Nothing in the solar wind maintains coherence at that scale. When frequency domain analysis was applied, the pulses formed discrete harmonic steps, 1.2, 2.4, and 4.8 millimerts. These are integer multiples, exact multiples of the base cycle observed in the object's luminescence. Nature rarely produces clean harmonics. Machines do. The signal's power curve also defies expectation. Magnetic waves from solar activity decay exponentially with distance, but these pulses fade logarithmically, a much slower drop-off, suggesting they're not simple emissions, but resonant waves constantly reinforced from their source. In a private joint session between NASA and ESA field scientists, Dr. Syra Hollingsworth reportedly asked a question that silenced the room. If this field is stable, then something's maintaining it. What's maintaining it? To answer that, analysts turned to vector mapping. By comparing the probe data from multiple spacecraft, they triangulated the approximate geometry of the field. What they found resembled a toroidal envelope, a magnetic ring surrounding the object extending several thousand kilometers outward. It's not a natural pattern. Comets can produce temporary magnetospheres through ion interaction, but those are chaotic, asymmetric, and short-lived. This one is symmetric, persistent, and aligned with the object's spin axis. Even more puzzling is its orientation. The field's north-south alignment doesn't correspond to the sun's. It's tilted 37 degrees, matching the angle of the object's own rotational plane. That alignment is too exact to be coincidence. Inside this magnetic envelope, plasma behaves differently. Parker's sensors detected a region of reduced particle velocity, a calm, hollow shell where solar wind particles slow dramatically as if being buffered. It's the same phenomenon seen around magnetically shielded spacecraft where charged fields deflect ionized particles. In other words, 3I Atlas seems to be protecting itself. To understand the strength of that field, the team modeled its potential source energy. The calculations were sobering. To maintain a 0.004 Gauss modulation at 0.48 astronomical units, the object would need to generate the equivalent of 10 to 10 joules per pulse, roughly the output of a large terrestrial power plant, repeating every 10 seconds. No geological process could sustain that. Still, the cautious language continues. NASA's provisional report refers to it as a localized magnetic coherence phenomenon. But between agencies, the phrasing has shifted. Artificial magnetic confinement. The implications are staggering. A field like this would not only shield the object from solar radiation, but also enable electromagnetic propulsion. Subtle adjustments in trajectory through Lorentz interaction with the solar plasma. That mechanism would explain why 3I Atlas's orbit remains unnaturally stable despite radiation pressure that should have altered its path weeks ago. Meanwhile, a group of independent astrophysicists at the University of Kyoto detected something even stranger. In the low-frequency radio spectrum between 20 and 30 kHz, a faint sideband appears each time the magnetic field peaks. The sideband drifts by exactly 41 Hz per cycle, as though the object's field is encoding data, frequency shift keying, but on a cosmic scale. The signal isn't strong enough to decode, and most experts still attribute it to harmonic interference. But a small subset of researchers, including plasma physicist Dr. Olivia Castens, has proposed that the sideband may represent a feedback signature, the magnetic field adjusting to external variables, responding dynamically rather than passively. If that's true, then 3I Atlas is sensing its environment and adapting. The prospect terrifies some scientists and exhilarates others. In an anonymous post to the Deep Space Network's internal message board, one engineer wrote, "It's not emitting a signal for us. It's tuning itself like something finding resonance in a larger field." The last confirmed magnetic pulse came through Parker's feed just hours ago. The amplitude hasn't faded. If anything, it's strengthening. The field coherence is climbing by roughly 1.7% per day, an exponential curve that will peak right around October 29th, the moment 3I Atlas disappears behind the sun. Whether coincidence or coordination, the timing feels deliberate. The field intensifies as the object moves out of sight, as if preparing for something hidden from direct observation. And as the magnetic hum grows stronger, the light itself begins to change color. The nickel-blue tones are fading, replaced by a deeper hue, one that no known natural process should produce under solar conditions. By October 25th, images from JWST and ESA's solar orbiter began showing a new kind of glow. The once steady nickel-blue luminescence, the same hue that had defined 3I Atlas for months, was dimming. In its place, analysts observed a darker iridescent hue hovering between emerald green and spectral violet, depending on the instrument. At first, it looked like a calibration glitch. Cameras don't lie, but they can confuse wavelength ranges under high flux. Yet, across 5 observatories and 3 separate instruments, the same change appeared. This wasn't a glitch. The color had shifted. Natural comets can change hue as they sublimate, shedding volatile compounds that fluoresce differently under ultraviolet light. Cyan, for instance, produces blue. Diatomic carbon gives off green. But in 3I Atlas, the shift didn't match any known gas emissions. Its spectral lines were too narrow, too discrete, clustering around 400, 520, and 670 nanometers, a perfect harmonic triad that doesn't occur in natural chemical spectra. When plotted against known elements, the emission peaks didn't align with carbon, hydrogen, or even metallic ions. They followed a mathematical pattern instead, a logarithmic spacing consistent with harmonic resonance, not chemistry. That's when physicists began suspecting something far more complex. The light wasn't merely emitted, it was being modulated. NASA's Visible Light Photometry division ran a detailed analysis, measuring phase angles between the spectral peaks. They found a precise phase offset of 72 degrees between each dominant color band, an offset corresponding exactly to the angular spacing of the object's outer fissures visible in the infrared images. In other words, the color change isn't random. It's structural, linked directly to the geometry of the body itself. That discovery led to a chilling hypothesis. 3I Atlas's surface could be acting like a photonic lattice, a material that manipulates light through internal interference. In engineered systems, photonic lattices are used to control color emission and reflection by altering the paths photons take through a crystalline grid. The concept has never been observed in a natural celestial body, and certainly not at kilometer scale. If accurate, this means 3I Atlas's color shift is not just a chemical reaction, it's a reconfiguration of its optical surface. Meanwhile, thermal and magnetic sensors registered something unexpected. As the color deepened, the object's overall energy emission dropped by nearly 15%. Yet the internal pulse cycle continued unaffected. It's as if the energy was being reabsorbed or redirected rather than radiated away. This coincided precisely with the magnetic field's rising coherence. To some, that suggests an unsettling possibility, that 3I Atlas is transitioning into a different energy state, storing incoming solar power instead of reflecting it. In laboratory plasma systems, this would be described as plasma inversion, where absorbed energy increases internal excitation rather than visible output. In an engineered system, it would look like charging. At the same time, independent amateur astronomers reported the same hue change in visible light. Using backyard telescopes equipped with diffraction gratings, they captured frames showing a faint green-violet flicker, repeating in the familiar 9.6-second rhythm. The fact that such modulation is visible even through atmospheric distortion suggests extraordinary brightness and precision. Several labs attempted to simulate the color pattern under controlled conditions. None succeeded. The only models that replicated the tri-band emission required electromagnetic interference grids, structures capable of shaping light at the subatomic level. That discovery forced analysts to confront an uncomfortable question. If the light is structured, what is shaping it? Dr. Marisa Karov, an optical physicist at the Czech Academy of Sciences, summarized the dilemma in a closed seminar. We are not seeing reflection, refraction, or emission in the traditional sense. We're seeing light behaving as if it's being told what to do. The hue deepening isn't uniform either. Along the fissure, the same diagonal scar that's been glowing for weeks, the green-violet blend intensifies dramatically, producing a pearlescent gradient unlike any observed albedo behavior. The gradient shifts spatially in sync with the object's rotation, as though rotating fields of light were sweeping across its surface. Curiously, this hue transformation coincides with the object's entry into a stronger solar field region. Around October 24th, the Interplanetary Magnetic Field, IMF, began tightening, funneling charged particles more directly along the ecliptic. Normally, this would brighten a comet's coma, but in this case, it darkened it, the opposite of expected physics. Some analysts believe 3I Atlas's magnetic envelope may now be absorbing photons, bending light into the surrounding plasma instead of scattering it. If true, 3I Atlas may be using light itself as a functional component, not merely reflecting it, but working with it. The phase-shifted color harmonics could represent transitions within a broader system, a change of operational state, or a response to the sun's approaching conjunction. But this brings up another troubling pattern, the timing. The color shift began almost precisely when Earth's line of sight began to close. By October 29th, 3I Atlas will vanish behind the sun for nearly 3 weeks. The color change started as visibility dropped, a synchronization too perfect to ignore. Coincidence? Possibly, but in astrophysics, coincidences that align with orbital blind spots are rarely comforting. What remains most perplexing is how deliberate the process seems. Nothing about it feels spontaneous or chaotic. The hues transition gradually, predictably, as if following an internal schedule. And that timing leads to the next puzzle, one buried not in color or geometry, but in the clockwork precision of the entire sequence. Because as 3I Atlas dims from blue to violet, its emissions, field, and motion all seem to obey a pattern, one aligned not with physics, but with time itself. When scientists compiled the latest telemetry from every active mission tracking 3I Atlas, a startling realization emerged. The data wasn't chaotic, it wasn't random. Nothing in known astrophysics behaves like that. A natural body can't maintain phase alignment across light, heat, magnetism, and motion unless those variables are coupled by design. In other words, the object systems, whatever they are, operate under a shared temporal regulator. The timing data becomes more unsettling when plotted against 3I Atlas's orbital position. Every ninth pulse corresponds to a microshift in the object's angular momentum, measurable through the jet's orientation changes. The effect is tiny, fractions of a degree, but perfectly rhythmic. Over hours, the pattern resembles a low-frequency oscillation, a steady heartbeat driving micro-course corrections, as if the object periodically adjusts its own alignment relative to the Sun. ESA's dynamics unit labeled it the Atlas interval. The phrase now appears in multiple mission logs, though no one has publicly acknowledged its meaning. Inside the solar physics laboratory at the University of Vienna, data scientists ran a Fourier transform across the full light curve dataset. The output revealed a secondary modulation. Every 3,600 cycles, a faint, slower wave overlays the signal, almost imperceptible, but real. That period equals 9.6 seconds x 3,600, 9.6 hours, nearly matching the half-rotation time of the object. In simpler terms, its internal pulses are synchronized not only moment to moment, but across its own spin. That's not natural resonance, that's timing architecture. Speculation began to spiral. Could the pulse represent thermal breathing, material expanding and contracting as it heats? Unlikely. Thermal cycles lag behind radiation input, yet the pulses are instantaneous. Could it be magnetic realignment? Possibly, but the field changes too sharply for diffusion. Could it be a feedback system, an internal regulator maintaining equilibrium? That's the only explanation that fits all data simultaneously. Dr. Irina Vogel, a systems engineer temporarily seconded from ESA's propulsion division, put it bluntly during a closed review: it's behaving like something that knows what time it is. Around the same time, independent astronomers noticed an additional correlation. The pulse frequency subtly accelerates by about 0.0003 seconds per day as the object approaches solar conjunction. Extrapolated forward, the cycle reaches exactly 9,000 seconds on October 29th, the moment it passes behind the Sun. A clean round number, perfect integer symmetry. That convergence is no coincidence. Natural periodicities drift with environment. They do not target mathematical neatness. But 3I Atlas's rhythm is converging toward precision, as if the system is preparing for a defined event that requires exact timing. If the pulse serves as a kind of internal clock, it could coordinate multiple functions: rotation, field modulation, energy cycling. But to what end? The simplest theory is stabilization, a self-regulating mechanism maintaining orientation before conjunction when solar interference peaks. A more speculative view suggests communication or synchronization, not with Earth, but with something else beyond the Sun's line of sight. Because in the last 72 hours, new readings show the pulse frequency coupling with the Sun's own oscillations. Helioseismic monitors recorded faint harmonic alignment between 3I Atlas's cycle and one of the Sun's natural acoustic modes at 3 MHz. It's as though the object is locking onto a solar rhythm. For NASA's data analysts, that was the moment the conversation changed. This is no longer about reflection, magnetism, or material composition. It's about timing, control, intent. The next question is who or what established that clock and why it's converging, exactly as the object slips behind the Sun into the one region where no Earth-based instrument can observe it. Because while the rest of the system hums at 9.6 seconds, the agencies themselves are facing a different kind of synchronization. Every instrument's data stream will soon go dark at once. And that's when the experts began arguing not about the signal itself, but about what it means and whether we're supposed to see it at all. By the morning of October 26th, the debate around Three-Eye Atlas had become a silent war inside the scientific community. Every major observatory had the same data, the same rhythm, the same impossible patterns, yet no one could agree on what to call it. Some still insisted on anomaly. Others whispered the word no one wanted to put in print: artificial. Inside NASA's Goddard Space Flight Center, a classified meeting stretched late into the night. 17 researchers, 3 engineers, and 2 agency liaisons gathered around a secure feed displaying synchronized telemetry from JWST, Parker, and Solar Orbiter. On the screen, Three-Eye Atlas's heartbeat pulsed across 4 graphs: light, magnetic field, temperature, rotation. 4 independent instruments, 1 perfect rhythm. The room was silent for long stretches. Then came the split. Dr. Janice Lung, an astrophysicist specializing in interstellar objects, argued, "First, this is a plasma resonance effect. The cycles could be harmonic feedback between solar magnetic lines and the object's metallic composition. There's no intelligence required for that." Across the table, her colleague Dr. Lewis Have countered, "Except that plasma feedback decays exponentially. This has increased in coherence, and it's maintaining exact timing to the millisecond. That's not resonance, that's control." Similar arguments were erupting across the world. The Max Planck Institute circulated a memo cautioning that anthropogenic interpretation, assuming intent behind the data, could bias the analysis. But behind the language of restraint, unease was spreading. In Cambridge, the Harvard-Smithsonian Astrophysical Center held a private round table where younger researchers openly challenged the older generation's caution. One postdoc summarized their position bluntly. "If this were a signal from a pulsar, we'd call it coherent emission. If it were a spacecraft, we'd call it controlled modulation. But because it's an object we didn't launch, we pretend it's random. That's not science, that's fear." Across the Atlantic, the European Space Agency's Optics Division issued a preliminary statement calling the light modulation a phenomenon of non-stochastic photometric periodicity. The phrase sounds technical, but internally one analyst admitted what it really meant: a repeating pattern that shouldn't exist. Even the SETI Institute, usually cautious to avoid sensationalism, joined the conversation. Their director of optical searches, Dr. Anwar Khatib, published an encrypted note to colleagues reading only, "This is not communication, it's calibration." That single sentence ignited a new wave of interpretation. If Three-Eye Atlas isn't signaling to us, perhaps it's synchronizing with something else, possibly the sun itself. The timing pattern, the magnetic resonance, and the phase lock could all serve one purpose: maintaining coherence with a larger energy field. But not everyone accepted the extraordinary explanation. A team from the University of Arizona, long considered the skeptical nucleus of the Three-Eye debate, released a preprint arguing that all anomalies could be modeled as the byproduct of a thin-disk interstellar origin. In their view, Three-Eye Atlas is a relic, a fragment of an ancient planetesimal ejected from the galactic thin disk millions of years ago, carrying metallic compounds capable of complex electromagnetic behavior. The appearance of regulation, they wrote, is an illusion born from coincident periodicities. Yet, when independent labs attempted to replicate their model, it failed to reproduce the coherence. Every simulation decayed, the real object doesn't. By late afternoon, the divide had hardened into factions. On one side, the naturalists insisting that even the strangest data must have a physical explanation rooted in chemistry, magnetism, and light. On the other, the systemists, a growing minority convinced that Three-Eye Atlas operates as a system, whether designed by intelligence or by an unknown natural process indistinguishable from it. The tone between them grew sharp. The systemists argued that refusing to confront the data was intellectual cowardice. The naturalists warned that jumping to conclusions could trigger the biggest misinterpretation in modern science. Neither side could disprove the other. Behind the scenes, administrators were losing patience. NASA's Public Affairs Office quietly drafted a non-statement, anticipating questions from journalists who had begun noticing irregular data releases. The line reads, "3I Atlas continues to exhibit unusual but naturally explainable characteristics under investigation." It's the same sentence template used during the Oumuamua controversy in 2017, but in private, researchers aren't convinced. One senior engineer leaked a single line from an internal Slack thread. "If this thing is natural, nature has started following blueprints." As the debate deepened, one mystery remained constant: gaps in the data, missing timestamps, truncated frames, unexplained file omissions. The most recent JWST packet skips precisely 57 seconds of observation, replaced by a checksum error. No official explanation has been given. For a community built on precision, those absences speak louder than the findings themselves. Because when the data starts disappearing, it usually means someone wants time to decide what to say next, and the silence only widens the divide. In the early hours of October 26th, a line appeared in NASA's Planetary Data System logs. Dataset Atlas 3I Vis SPC 1025-1024 temporarily restricted pending validation. It was a single sentence automatically generated, buried deep within the database. But for those watching closely, it marked the moment the silence began. By midday, researchers attempting to access the October 24th composite files found them replaced with blank stubs. File names intact, but data stripped. The checksum values remained, implying the files once existed. They simply weren't accessible anymore. At first, the explanation was procedural. A NASA spokesperson described it as a data sanitation event, part of routine cross-mission calibration. Yet that phrase, data sanitation, appears nowhere in official documentation. When pressed, the agency declined to comment further. Within hours, other anomalies followed. JWST's normally continuous observation log contained two gaps, 0311 to 03.12 UTC and 0546 to 05.47 UTC, each gap exactly 1 minute long. ESA's solar orbiter reported similar missing telemetry, also in 1 minute intervals, both aligning with the 9.6-second emission cycle, precisely 6 pulses per minute. In total, nearly an hour of coordinated observation time vanished across 3 separate missions. To the untrained eye, it's a small loss, but in deep space observation, a single minute is priceless. When multiple instruments simultaneously go dark in equal blocks, the pattern itself becomes evidence. Behind the scenes, scientists began asking questions they weren't supposed to. The first suspicion, data suppression. Was something captured during those missing intervals that agencies didn't want released? Dr. Ahmed Faiz, a data systems engineer at ESA, summarized the frustration in a private forum. "You can't sanitize raw FITS files. Once they're uploaded, they're immutable unless someone deliberately removes them." Around the same time, the Solar Dynamics Observatory, SDO, unexpectedly halted one of its ultraviolet channels for recalibration. The downtime lasted exactly 57 minutes, identical to the total duration of missing frames from the 3I Atlas dataset. Statistically improbable, operationally suspicious. By the evening of October 26th, independent archivists noticed another pattern. The missing intervals corresponded not just to the object's activity peaks, but to its angular alignment with the sun's corona, the point when light reflection, thermal spikes, and magnetic modulation converge most intensely. In other words, the data vanished exactly when 3I Atlas was doing something unusual. NASA's external data mirror, hosted at the Goddard DAC, displayed a new access flag, Restricted Protocol 14. Few outside the agency know what Protocol 14 means, but insiders recall it being used only twice before, once during the Parker probe's 2022 perihelion event, and once during the classified Oumuamua post-analysis in 2018. Both cases involved sensor anomalies deemed non-naturally correlated. ESA followed suit. Their own data portal briefly displayed the note, "Delayed publication pending cross-agency verification," before removing it entirely. At this point, the information gap became impossible to ignore. Scientists outside the official pipeline began reconstructing what was missing using mathematical interpolation. They took the surrounding frames, filled the gaps with predictive modeling, and found a spike. A brief but dramatic surge in reflected intensity precisely where the data cuts off. For approximately 0.4 seconds, the object's apparent brightness tripled, then returned to normal. That flash wasn't random noise. Its signature carried harmonic coherence identical to the magnetic pulse. If real, it represents the strongest single-emission 3-eye atlas has ever produced. And it's the one moment that no official archive will show. The implications were immediate. Was the flash a burst of stored energy, a reaction to solar interference, or something triggered deliberately as it entered the last phase before conjunction? Even among cautious scientists, the silence was deafening. Some called it bureaucracy, others called it containment. Either way, the narrative shifted. For months, the world has been told that 3-eye Atlas is under routine observation, a scientific curiosity, nothing more. But as the blind spot approaches, communication grows vague. Language turns clinical, and data disappears. The public, of course, notices nothing. No press conferences, no briefings, no leaks to major outlets. The story has been buried under the noise of daily news, but inside observatories, the absence is all anyone talks about. As one astrophysicist wrote anonymously in an internal Slack thread, "The only thing louder than this object's signal is the effort to make it quiet." And still, the magnetic pulse continues to rise. The timing tightens. The light grows more coherent. The entire system appears to be building towards something, a change, a transition, or a maneuver. And the only instruments capable of recording it will soon be staring straight into the sun. The next chapter examines the few remaining fragments of motion data that escaped the blackout and how they suggest something even more unsettling. 3-eye Atlas may not be holding its course anymore. At 1942 UTC on October 25th, the Solar Orbiter's onboard heliospheric imager caught something odd at the edge of its frame, a streak, faint but clean, extending diagonally from 3-eye Atlas's predicted path. It wasn't a flare artifact or cosmic ray hit. Those have chaotic signatures. This line was smooth, continuous, and curved. That's equivalent to a shift of nearly 13,000 kilometers at its current distance. To most, that's negligible. To mission analysts, it's seismic. A natural comet doesn't just slide sideways against gravitational flow, especially not one under such close solar influence. At first, teams blamed the instruments, sensor drift, timing error, even software calibration. But cross-verification crushed those theories quickly. Both SOHO's LASCO C3 and Bepi Colombo's plasma monitor showed the same lateral displacement confirmed to within 3 arcseconds. The readings matched across independent spacecraft separated by millions of kilometers. The shift was real. At the same moment, the magnetic pulse amplitude spiked, rising by 7% above baseline. The heat curve dipped slightly as though the object had vented energy, and then, like clockwork, the jet geometry realigned. It wasn't just drifting, it was correcting. When plotted over time, the pattern looks deliberate, a sequence of micro-adjustments forming a smooth, arcing trail. Analysts called it the Atlas loop. The movement wasn't linear but orbital, a shallow curvature inward, closer to the sun. Yet even that's a problem. At this phase of its trajectory, gravitational acceleration should push 3I Atlas away from the solar surface, not toward it. Something else was applying force. In internal simulations, engineers tried everything: outgassing, asymmetrical heating, plasma drag. None matched the acceleration profile. The only fit came when they added a small, consistent thrust vector aligned with the object's internal jet, one generating just 0.5 newtons of force. An insignificant push by human standards, but over time enough to account for the deviation exactly. That's not coincidence. That's propulsion. If this is true, it means that for at least the past 72 hours, 3I Atlas has been maneuvering, not tumbling through space, not obeying random solar forces, but steering. This idea isn't without precedent. When Oumuamua passed through the inner solar system in 2017, it too exhibited non-gravitational acceleration. Back then, scientists proposed exotic explanations: outgassing we couldn't see, pressure from sunlight, even thin-sheet physics. But 3I Atlas is different. It's visible, it's active. Its thrust correlates with its internal cycles. That's where the debate turns dangerous, because if these course changes are deliberate, then the timing matters. The first deviation began right after the missing data window, the same gap NASA and ESA labeled under review. The next occurred 12 hours later, coinciding exactly with a new thermal pulse peak. The third, the largest, happened just as the magnetic envelope strengthened to its highest measured coherence. Each event forms part of a pattern: pulse, field spike, minor course correction. When superimposed, those corrections trace a path bending inward toward a tighter solar approach. On October 29th, the day of conjunction, the new vector would take 3I Atlas 15,000 Talos kilons closer to the Sun than predicted, skimming the upper corona before vanishing behind it. That change defies explanation. Why would any object, natural or otherwise, move toward a star's surface at that proximity? Some analysts propose that it's gravitational focusing, a fluke trajectory adjustment. Others quietly admit what the math implies. The object is setting up for something. At ESA's mission control in Darmstadt, a closed-door session convened to address trajectory deviations in Atlas 3I. Notes from that meeting, later leaked, reveal a chilling exchange. If it's outgassing, it should accelerate irregularly, one engineer said. It doesn't, another replied. Then it's guidance, came the quiet answer. Why now? Why release official images days before conjunction only to retract them? Why go silent just as the motion changes begin? The answer might lie in timing, because behind every missing frame and every quiet update, there's a clock, not just the 9.6-second pulse, but an institutional one. A countdown agencies won't acknowledge, but one every analyst can feel. 3 days until 3I Atlas disappears behind the Sun. When it does, no human instrument will see it again until late November. And whatever happens during those 3 invisible weeks may decide what kind of story 3I Atlas truly is. A natural wanderer caught in solar currents, or something quietly using the Sun itself as part of its design. Every data set that remains, every pulse still echoing through solar space points toward coordination. The heat, the light, the field, the motion, all synchronized, all converging on one event. Solar conjunction, October 29th, 2025. At first, the simplest interpretation was orbital coincidence, a natural alignment between the object's inbound trajectory and the Sun. But orbital coincidence doesn't explain deliberate course correction, coherent magnetic shielding, or precision timing converging on a round integer of seconds. 3I Atlas isn't falling by chance, it's arriving on schedule. To many inside the agencies, the pattern now looks unmistakable. Every action the object has taken appears to prepare it for something that can only happen behind the Sun, in the one place no instrument on or near Earth can see. Some physicists propose that 3I Atlas is using the Sun itself as a power source. Its magnetic envelope and reflective geometry could enable a form of photonic accumulation, absorbing radiation, converting it, and storing it as structured energy. The color shift from blue to violet might signify the process of saturation, a change in emission frequency as internal energy builds. If true, conjunction would mark the phase of maximum input when the Sun's radiation pressure and magnetic field align perfectly with the object's orientation. In other words, the object could be charging. But charging for what? No one can say. Others see communication. The 9.6-second pulse synchronized across heat, light, and magnetism may not be an internal system at all, but a transmission protocol. The convergence toward a 9,000-second interval at conjunction could represent synchronization with an external source, perhaps solar, perhaps interstellar. In this model, the Sun isn't just a light source. It's a carrier. The object could be using solar plasma as a medium, embedding data or commands within magnetoacoustic waves that propagate through the heliosphere. The missing data blocks from October 24th to 25th might have captured the first fragments of this interaction before they were withheld or erased. To believers in this idea, 3I Atlas is a relay node, a transceiver awakening after centuries of dormancy, aligning itself with the Sun to send or receive something. A quieter minority offers another theory, that 3I Atlas isn't communicating or charging, but simply watching. Its motion toward the Sun could serve a geometric purpose, using the star's gravity as a lens. This would place the object at a precise focal distance, where sunlight bent by the Sun, its curvature can magnify signals from beyond the solar system. If this is true, 3I Atlas may not be performing. It may be listening. The timing patterns could be calibrations, aligning internal sensors to the gravitational focal line. Behind the Sun, shielded from direct detection, it would have an unobstructed view of deep interstellar space through the most powerful natural lens known, the Sun itself. In that light, conjunction isn't concealment, it's observation. Then there's the most troubling interpretation, the one no one wants to say aloud, that the course corrections are not preparation for a single event, but for a re-entry. If the trajectory models are accurate, 3I Atlas's path after conjunction will not lead outward back into the void. It will bend slightly inward, looping around the Sun and emerging again toward the inner solar system, closer this time, slower, lower in inclination. That's not escape, that's approach. Every data model that includes the new thrust vector shows the same outcome. By mid-December, the object could reappear on the daylight side of the Sun, passing within 0.9 astronomical units near Earth's orbital zone. If so, the intent might be simple: positioning, using the Sun's gravity as a slingshot, aligning its field, recalibrating its systems, and then descending into a region where electromagnetic interference drops low enough for direct observation or contact. No one can verify that yet, and until the Sun releases its grip, no one will. Agencies have gone quiet. ESA cancelled the joint press briefing planned for October 28th. NASA's Solar Dynamics Observatory has locked its ultraviolet feed. The James Webb tracking schedule now lists instrument cool-down maintenance during conjunction, a convenient cover for pointed unavailability. In private channels, some researchers still exchange encrypted notes, sharing fragments of new telemetry and attempting to model what happens next, but most have stopped talking. One message sent anonymously to a scientific listserv summed up the atmosphere in 5 words: "It's not moving randomly anymore." For now, all anyone can do is wait. The object will vanish behind the Sun in less than 72 hours. No light, no magnetism, no signal will reach us during that time. When it re-emerges, one of 2 things will happen. Either it will continue on a natural outbound arc, and the story will fade as another misunderstood anomaly, or its vector will shift again, slower, lower, closer. If that happens, the argument about intent will end, because then the question will no longer be what Three-Eye Atlas is, it will be who it's coming for. By late October 26th, the live feeds narrow to static. The optical arrays that once sent crisp images of Three-Eye Atlas now capture only interference bands, blurred arcs of light at the edge of the sun's glare. It isn't that the object has vanished yet, it's that every system watching it has begun to shut its eyes. At NASA's Deep Space Network station in Canberra, technicians watch the last confirmed signal fade from the solar orbiter's telemetry feed. The object's pulse, steady for months, is still present but fainter. Its amplitude down by 60%, its wavelength stretched thin by solar proximity. "We're losing the heartbeat," one engineer mutters. Across the Atlantic in Darmstadt, the ESA command center mirrors the same pattern. Magnetic coherence readings continue to rise, yet visual brightness falls. The paradox makes sense only if the object is folding its field inward, conserving energy, contracting light as though preparing for something that demands silence. The language in internal reports grows measured, hesitant. Phrases like sustained internal resonance and temporary communication blackout replace the word anomaly. Everyone knows what's happening, but no one wants to be the first to say it. The object isn't just drifting behind the sun, it's withdrawing. Even the data that remains carries an eerie stillness. The rhythmic 9.6-second pulses begin to slow, not irregularly but methodically, each beat lengthening by microseconds like a system powering down. By midnight UTC, it stabilizes at exactly 10 seconds, round, deliberate, final. A few scientists believe this slowdown marks the end of its active phase. Others think it is synchronization. The moment the object locks into the solar cycle, it has been echoing for weeks. Either way, the pattern holds and then stops. The last confirmed pulse reaches Earth at 3:19 UTC, October 27th. After that, only noise. For the first time since its discovery, Three-Eye Atlas is unobservable. Its vector now carries it behind the sun into a region where light cannot pass, radio cannot penetrate, and our most advanced instruments are blind. The quiet window, as NASA calls it, will last until at least November 18th, when it's expected to re-emerge. Between now and then, there's nothing to do but wait. Still, in private, few believe the agencies are truly powerless. Rumors circulate of deep space relays capable of indirect observation through neutrino flux, detectors that might still track the object's magnetic outline even through solar interference. If such systems exist, no one will confirm it. The official record will remain blank, a seamless wall of absence, and yet the absence feels intentional. Every scientist who's followed Three-Eye Atlas feels it, an unease that something meant for us to look and now means for us not to. One final document circulates through the internal channels of the European Southern Observatory. Unsigned, timestamped 4:11 UTC. It reads, "Only do not assume conjunction equals disappearance. Assume phase transition." No one knows who wrote it. The message vanishes from the server minutes later. Now the countdown is no longer to an observation. It's to a reappearance. When Three-Eye Atlas emerges from the far side of the sun, it will either return to its predicted path, silent, cooling, natural, or it will come back altered, its field stronger, its trajectory inexplicably changed. If that happens, the conversation about what this object is will end. The universe will have given its answer. But for now, as the signal fades and the light dissolves into the sun's glare, the only certainty left is silence, and a single unfinished line in an internal log at Goddard. Cycle complete. Await next phase. And if it doesn't reappear, Three-Eye Atlas will become something rarer than an anomaly. It will become a myth in data form, a record of something seen, measured, and then lost. An event that left no tail, no debris, no trace except the faint gravitational scars it carved into our models of reality. Either way, next contact will not be the end of this story. It will simply be the handover point between observation and memory, the moment when one chapter of the universe closes its eyes and another, still unwritten, begins to breathe. In the beginning, it was just a point of light, a distant faint anomaly caught in the margins of a telescope's field. Then came the echoes, the cluster, the gravitational drift, the silence. And now, a waiting world stands on the edge of recontact, watching for something it cannot see. 3I Atlas has never behaved like an ordinary object. It has moved through the solar system with quiet precision, threading through gravitational corridors as though it understood their geometry better than we did. Its silence has been more eloquent than the noise of any comet's tail. It has refused to flare, refused to fracture, refused to explain itself. It simply moved. And now it waits behind the sun in the blackout, in the place where observation ends and speculation takes over. The network tracking this object isn't just one organization or one nation. It is a web stretched across the planet. Observatories, radar stations, infrared arrays, solar monitors, gravitational models, academic papers written under flickering labs. Most of them don't speak to each other directly. They don't need to. The object itself has bound them into a quiet, involuntary collaboration, a shadow network built around something no one fully understands. In the coming days, the first signals will return, perhaps a faint streak of light, perhaps a radar echo, perhaps nothing at all. But whatever emerges from behind the sun will set the shape of everything that follows, not just the trajectory of the object, but the trajectory of our understanding of what moves through interstellar space. If the formation holds its geometry, it will redefine stability in high-energy celestial environments. If it fragments, it will confirm the sun's relentless authority over even the strangest visitors. If it vanishes, it will leave behind a gravitational whisper, an absence louder than its presence ever was. This is what cosmic mysteries do. They don't just challenge science. They connect institutions, stretch instruments to their limits, and leave stories written in equations long after the skies have cleared. They remind us how fragile our certainty is and how much of the universe still moves in shadow, just beyond the reach of our senses. The world won't see a spectacle when 3I Atlas re-emerges. There will be no blazing tail, no brilliant sky event. There may only be a dim, silent point flickering through the last strands of solar glare. But behind that point will be weeks of silence, months of argument, years of analysis, and the uneasy recognition that something crossed our star and told us nothing. The shadow network will remain even after the object drifts back into the dark between stars. Datasets will be stored, orbital models will be refined, every anomaly will be catalogued, and future generations may look back at this event not as an answer, but as a beginning. A quiet sign that not everything moving through the void behaves the way we expect. The story of 3I Atlas does not end with reappearance. It ends with a question suspended in space. How many others are passing through in silence right now? The instruments will stay pointed at the sky. The algorithms will keep listening. The shadow will move on, and the silence it leaves behind will echo for years.